5 days online. Good afternoon everyone. Welcome to the second session of day 3 of 5 days online IST approved faculty development program on recent advances in RF and microelectronics organized by Department of Electronics and Telecommunication, Don Bosco College of Engineering, Goa, and Department of Electronics and Communication Engineering, National Institute of Technology, Goa. Technically sponsored by IEEE Bombay Section, WIE Affinity Group. Our resource person for this session is Dr. Hassan Ali Virani. He has completed his BE from Goa University in Electronics and Telecommunication Engineering in August 1991. He has completed his MTech in Industrial Electronics from NIT Karnataka in 2004 and completed his PhD from IIT Bombay in 2012. He is at present serving as Professor and Head of Department of Electronics and Telecommunication Engineering at Goa Engineering College, Farmagudi, Goa. He has 26 years of teaching experience and 3 years in telecom industry. He has total of 145 research publications. He has guided 60 master's degree projects. He is a chairman of IETE Goa Sub-Center from 2014 till date. Besides this, he is also a member of different professional bodies like Institute of Engineers and Indian Society of Technical Education. He has worked in the areas of device design and simulation, VLSI design, image processing, microstrip antenna design, wireless and data communication. We welcome you, sir. I request sir to take over the session.
Good afternoon everyone and welcome to this session on Trends in Integrated Circuit Technology, a Device Perspective. I am Dr. Hassan Ali Virani from Department of Electronics and Telecommunication Engineering, Goa College of Engineering, Farmagudi, Goa. The area of microelectronics can be broadly divided into two parts. First is the design of the integrated circuit, which is also popularly known as VLSI design. And second is the technology required to make the integrated circuits. The technology part can be further subdivided into two parts. One is the fabrication techniques that are required to make the integrated circuits, and second are the devices which are required to make the integrated circuits. In this session, we will be talking about the devices. To understand the importance of devices, we will compare it with a vehicle. A vehicle has an engine and a body. The engine determines the power generated, the fuel consumed, and the performance of the vehicle, whereas the body decides the functionality of the vehicle. If the body is made like a car, then it transports passengers. If the body is made like a truck, then it transports goods. Similarly, devices are engines of integrated circuits. They decide the current driving capacity, the power consumed, and the speed of the integrated circuits. Whereas the circuit design determines the functionality of the integrated circuit. Therefore, devices act as engines powering the integrated circuit. This is a brief outline of my presentation. We will first understand the historical background, followed by evolution of devices and IC. Then we will look at the understanding of ITRS, physical limits in scaling MOSFET and possible solutions, extending CMOS, a revolutionary approach, MOSFET alternatives, scaling of interconnection, and finally the conclusion. If we look at the historical background, the first device that was made was a vacuum tube, also called as electronic tube or thermionic valve or simply a valve. It is a device which controls the electric current through a vacuum in a sealed container, also known as addition effects. These are the images of the various vacuum tubes. Vacuum tubes are used for rectification, amplification, switching, and even creation of electrical signals such as oscillators. It was widely used in 1970s for radio broadcast, radio receivers, radars, sound recording, telephone networks, and industrial process control. The World War II time, a lot of research was done which helped us in producing extremely pure germanium crystals, point contact mixer diodes for use in radar, and the first solid state diode was developed by Bell Labs using the germanium crystals which were produced at Purdue University, USA. These devices worked much faster than the vacuum diodes. After the World War II, William Shockley proposed to attempt the building of a triode-like semiconductor device. He secured funding and the lab space and went to work on this problem with Bardeen and Bretin. The first transistor was invented by these three, that is John Bardeen, Walter Bradin, and William Shockley in 1947. It was a germanium point contact transistor. The input current creates a P region that modulates the output current very close to the gold foils shown in the figure. In 1950s, the need for miniaturization increased for applications like hearing aid. In 1953, a miniaturized hearing aid was made using 5 transistors. In the mid-50s, several companies started mass production of the transistors. And in 1953, Texas Instruments commercially produced silicon transistors. The images show the sub-mini tubes used in a hearing aid and the germanium transistors which were used for the hearing aid. William Shockley left the Bell Labs in 1954 and started his own company called Silicon Valley. Two young engineers, Murray and Noisy, joined the Shockley's company. Later, Murray and Noisy set up a company called Fairchild in 1957. And in 1958, Fairchild introduced the new Planar technology. In 1958, the first integrated circuit was made by Jack Kilby from Texas Instruments. All the parts made out of the same block of material. Metal wires were used to interconnect the components. No discrete components were used. Kilby received the Nobel Prize in Physics for this work in the year 2000. He led the team of TI later for developing a handheld calculator. In the same year, the first integrated circuit was made in Fairchild. Noisy, who was a co-founder of Fairchild and later co-founder of Intel, came up with his own idea of IC around half a year later than Kilby. His chip solved many practical problems such as use of evaporated aluminum for interconnect in place of wire which were used by Kilby. Produced at the Fairchild Semiconductor, It was made of silicon, whereas Kilby's chip was made of germanium. In 1959, the first planar transistor was made at Fairchild. In 1961, the first commercially available integrated circuit was made by Robert Noisy, and it was a flip-flop circuit. In 1962, the NPN planar transistor was formed, again at Fairchild. In 1962 to 1964, the diode logic and the RTL logic gained momentum, and the circuits with this implementation was available as integrated circuits, as you can see in the figure. In 1963, the TTL logic family was introduced and available in different packages by major companies like Fairchild, Motorola, Philips, etc. In 1965, the Fairchild company manufactured the first commercial operational amplifier IC. This is the circuit schematic made up of bipolar junction transistors. This circuit was packaged in a flat pack IC as shown in the figure. Later, the same circuit was packaged in a PIN package with which we are all familiar. In 1960, the first MOSFET was made by Kang and Atala. The major difficulty in the manufacturing of MOSFET was the interface states at the top of the silicon wafer. With hydrogen annealing, he managed to reduce this interface state and make the gate stack that is required for the MOSFET. You have the silicon wafer on which he deposited the silicon oxide and deposited aluminum on top of SiO2. The silicon-silicon oxide interface is exceptionally good. The making of this MOSFET revolutionized the IC fabrication. MOSFET working is very simple. There is no gate voltage applied, no current flows between the source and drain. When a positive gate voltage is applied, inversion layer is formed which connects the source and the drain, and the current flows, turning on the MOSFET. The basic building blocks NMOS and PMOS gave rise to the CMOS integrated circuit family. In every CMOS, you have equal number of NMOS and equal number of PMOS. For example, in the CMOS inverter, you have one NMOS and one PMOS. In a NAND gate, you have two NMOS and two PMOS. In 1970 and 71, the Intel manufactured the first microprocessor 4004 and the DRAM 1103. This was the first generation of the large-scale integration. The technology node was 10 micrometer. The processor had 2300 transistors and worked at 64 kHz clock speed. In a small scale integration, the number of devices are typically around 1 to 100. Can perform functions like gates, op-amps, and linear applications. In medium scale integration, the device count is 100 to 1000 and can perform functions like the register, filter, etc. For large scale integration, the device count is 1000 to 1 lakh and can perform functions like microprocessor, analog to digital converter, etc. For very large scale integration, the device count is in between 10 raised to 5 to 10 raised to 6 and can perform functions like the microprocessor, memories and computer motherboards. For very large scale integration, the device count is greater than 10 raised to 6 and performs functions like memory and microprocessors. In 1965, Gordon Murray, who was a director of Fairchild Corporation and later who also co-founded Intel, he observed that in every 2 years, the number of devices on the IC doubled. This observation came to be known as Murray's law. As we can see in the graph, from 1971 to 2011, the number of devices on the IC went on doubling as per the Murray's law, and we got better and better microprocessors. Compared to the development of the IC technology, the Ferrari engine development was very less. This is the image of Intel Pentium 4, which was made in 2001. The technology node was 0.18 micrometer and had 42 million components on it. It worked at 2 GHz speeds and the interconnect size was typically around 2 kilometers. The ICs evolved from 1971 onwards to 2002, which is shown in the diagram. In 1971, Intel 4004 was manufactured, which is shown here in a small square, and in 2002, the Itanium was manufactured, which is shown here, and it is overlapping a 2-cent coin. So microprocessors and the integrated circuits evolved over the years, giving us better features and better performance. In the year 1971, 4004 processor was manufactured, having a feature size of 10 micrometer, die size of 12 mm square, transistor count of 2300, clock speed of 108 kHz and performed at 0.01 second speed. This is the 4004. Then the processor codename McKinley was manufactured in 2002. The feature size was 180 nanometer. Die size was 421 mm square. It had 221 into 10 raised to the power of 6 transistors on the chip and worked at 1 GHz. In 2005, the microprocessor codename Monticino was manufactured with a feature size of 90 nanometer. Transistors were 1.7 into 10 raised to the power of 9 and operated at 1.6 GHz. So the scaling of MOSFETs helped us to make better microprocessors, better interconnects and faster integrated circuits. Blue box here shows you the size of the interconnect for 4004 IC. The small squares here within this big square shows you the size of the interconnect for the McKinley processor. IC technology scaling. Why do we want to scale the transistor? Why smaller transistors are better? Scaling improves performance. First order scaling theory tells you that the dimensions as well as the voltage are scaled by a factor of S. This results into decrease in the intrinsic delay, power per transistor and power delay product. If we take 1971 as the reference, say S is equal to 1 year, in 1982 we could make smaller transistors and scale it by a factor of 5. In 2005 we could scale it down further and the scaling factor was 100. In 2010 we could scale it further and the scaling factor became 2000 and this process continued. Making smaller ICs helped us to make smaller computers. If you see here, in 1946, the first computer was Electronic Numerical Integrator and Calculator known as ENIAC. The size of this computer was that of a very big room. The weight was 30,000 kgs. It was made up of 18,000 vacuum tubes and could perform 5,000 additions per second. The input and output was in terms of punch cards and had to do manual operations, and the cost was $5 lakh. However, in 2013, we could make a small tablet PC as shown in the figure. It has a very small dimension. The weight is 2.1 kg, had more than 1 million transistors and costed us only $1,300. Computers has scaled over the years due to the scaling of CMOS. CMOS scaling has been the enabler of IC industry. Summarizing, this is the time frame of evolution of the integrated circuits. Between 1940 to 1950, the BJT transistor was fabricated, which gave us our first electronic computer. Between 1950 to 1960, the first integrated circuit was made, which helped us to give us a transistor based computer and then an IC based computer. In 1960, we got a silicon MOSFET which gave rise to the CMOS family, and that gave us the IC based computer. In 1965, Murray gave his famous Murray's law, and one transistor DRAMs ICs were made. In 1970, microprocessors gained momentum and MOSFET scaling theory evolved. From 1980 onwards, the scaling became very rapid and the very large scale integrated era began. Beyond 2000, we had the ultra large scale integration era. This graph depicts the achievement versus the Murray's law. This green curve here are the actual data, and the violet line here depicts the prediction as per the Murray's law. The red curve here depicts the development of DRAMs, and the yellow line here depicts the development of the microprocessor. As we can see, the development of the processors as well as the memory has kept in pace with the Murray's law. Let us have a closer look at scaling. Initially, the scaling was done in a uniform manner, also known as constant field scaling. Here, the bigger device was converted into a smaller device, scaling the physical and electrical parameters by a factor of k. Advantages were speed increased by a factor of k, area and power decreased by a factor of 1 by k, and the electric field within the device remained constant. However, it was noticed voltage scaled at a slower rate than the dimension. This resulted into non-uniform scaling. The reasons were because of the existence of different industry standards. The reasons were the reluctance to give up the extra performance advantage which we get at a higher voltage. So the threshold voltage could not be lowered any further because VDD minus VT determines the dynamic range, and the lowering of the threshold voltage increased the off currents of the MOSFET. Bit length has scaled down much more than the wiring. We come to the modified scaling rule. Additional scaling factor is used for the electric field, which means that VDD is scaled lesser compared to the physical dimensions. Two spatial dimensions are used for scaling. Alpha S for scaling the gate length and alpha W for scaling the device width and wiring. As a result of this non-uniform scaling, gate delay is scaled faster as compared to the previous rules. Coordinated efforts of industry was required to meet the common goal of miniaturization or scaling. Multiple developments in the process and design of devices were required to achieve this increased density. These improvements was summarized by the International Technology Roadmap for Semiconductor, also known as ITRS. Design tools improved enough to make it practical to finish this design in a reasonable time frame. ITRS is made up of 5 associations: Japan Electronic and Information Technology Industry Association, Semiconductor Industry Association from USA, Korea Semiconductor Industry Association, European Electronic Component Association, and Taiwan Semiconductor Industry Association. ITRS gives us a roadmap periodically since 1994. This roadmap is based on the past industry trend, which is based on Moore's law. The projection 2020 was that the gate length will become 9 nanometers and the clock speed will be around 40 gigahertz. In reality, we have achieved a gate length of around 15 to 10 nanometers and a clock speed of around 5 to 8 gigahertz. ITRS also gives us the specification of devices based on applications. It has divided the devices into 3 categories. First is the LSTP devices or the low standby power devices. Second is the high power or high performance devices. Third is the low operating power devices. The low stand power devices are typically the ones which are used in mobile applications which run on battery. In order to save the battery, the off current of the MOSFET has to be low so that the static power consumed by the CMOS circuit reduces. High performance devices are used typically in servers and high-end computers. These computers are connected to the mains, so there is no shortage of power supply. What is required is that the computer should give you faster performance. So the off current can be high and more importantly the on current should be high. Last category is the low operating power. Typical examples of this is the devices used in your calculators, in your watches. You put one battery and it runs for approximately 1 year because it is operating on low power. Here both the VDD is low and the I-off is low. ITRS technology defines the technology node as DRAM half pitch. As we can see here, between two metal layers, the metal pitch is defined and half of that determines the minimum feature size that you can make on the wafer. So the technology node definition is half DRAM pitch, half polysilicon pitch. These are the two polysilicon layers, polysilicon pitch. Half of that is the minimum feature which we can make on the IC. So the technology generations are defined by the DRAM half pitch. The gate lengths are typically less than equal to 0.5 into DRAM half pitch. This has been made possible because of the advancement in the fabrication technology. The rapid scaling of the gate length is driven by a need to improve the transistor speed. The clock frequency and functions per chip scale rapidly, but the allowable power dissipation rises slowly with scaling. This is limited by the ability to remove the heat from the IC. This graph depicts the various technology nodes that evolved from 1990 to 2010. As we can see, up to 0.35 micrometer node, both the gate length and the technology node had the same dimensions. Further, for 0.25 micrometer node, the gate length was 0.2 micrometer, that is less than the technology node. This process continues, and at 30 nanometer node we have a gate length of 50 nanometer. For every successive node, dimensions are scaled by a factor of 30%, which doubles the transistor density in the same area. Oxide thickness scales down, which gives us faster transistors and higher performance. VDD and VT is scaled, though not proportionately, but this helps us to lower the active power. The question is, technology has scaled well. Will it continue to do that in future? It's an example of how microprocessors have evolved over a period of time. The Intel 386 processor was initially made at a technology node of 1.5 micrometer, and this was the size of that processor. The same processor was then manufactured at 1.0 micrometer technology node, and the size of the processor reduced as we can see here. Similarly, 486 microprocessor manufactured at 1 micrometer node had this size. The same processor manufactured at 0.8 micrometer node had a smaller size. At 0.6 micrometer node had even a smaller size. Same holds good for the Pentium processor and the Pentium 2 processor. Let us try to understand the generations of Intel processors. Many people think Core i3, i5, i7, i9 are the generations of Intel. However, they are not. They are the brands or brand names of the processors from Intel. The major processors are Celeron, Pentium M and Celeron M, which are used for mobile PCs, which are battery operated, and it's specially designed with LSTP devices to save on power. Pentium Dual Core, Core Solo, Core 2, Core 2 Duo, Core 2 Quad, and the i3, i5 and i7, i9 with which we are familiar. What does the generation mean? A generation implies the change in a processor's architecture. The difference between two generations is in their microarchitecture. The generations are also known by the manufacturing codenames. The microarchitecture design involves pipeline depth, branch prediction, preemptive caching mechanism, cache coherence protocols, memory controllers, and parallelism. First generation was named Nehalem. It was released in November 11, 2008 and was manufactured using the 45 nanometer process as compared to the 65 nanometer and 90 nanometer process used previously. The cache sizes were L1 is 64 kilobytes, L2 is 256 kilobytes per core, and L3 is in the range of 4 megabytes to 12 megabytes, and it is shared. It reintroduced the concept of hyperthreading, which is nothing else but the clever way of scheduling tasks. This is the die photo of the first generation Nehalem processor. As you can see, multiple cores and three cache is shared. Second generation was codenamed Sandy Bridge. It was released in January 9, 2011. It was manufactured using the 32 nanometer process and had 14 to 19 stage instruction pipeline. It gave a 11.3% improvement in performance compared to Nehalem. The cache sizes were L1 was 64, L2 was 256 and L3 was 1 megabyte to 8 megabyte, again shared, and for the extreme processors it was 10 megabytes to 15 megabytes, again shared. This is the die photo of second generation processor. See the various cores shared cache in graphic processor was included in the die. Third generation was codenamed Ivy Bridge, released in 2012 and manufactured using the 22 nanometer process. It consumed 50% less power and 25 to 68 increment in performance. The cache sizes of L1, L2 are the same. L3 has slightly increased. This is the die shot of the third generation. Again, we see the various cores here, shared L3 and the bigger graphic processor. Fourth generation was codenamed Haswell, released in 2013 using 22 nanometer tri-gate transistor process. It gave an improvement in performance of around 3 to 8% and 5% faster single-threaded performance improvement. Again here, L1 and L2 cache size remains the same. L3's cache size increased and is shared. We can see the various cores of the processor, the cache memory and the GPU. It is the graphic processing unit. Fifth generation was Broadwell, released in 2014. It was manufactured using the 14 nanometer tri-gate process. The cache size increased in this. L1 was 64 kilobyte, L2 was 256 kilobyte, L3 was 2 megabytes to 6 megabyte shared. This is the die shot of the processor. You can see the cores shared L3, the graphic processor size has increased. Sixth generation was the Skylake, released in 2015, manufactured using 14 nanometer bulk silicon 3D transistors. Cache sizes are 64 and 256 KB. L3 size was megabyte. For the Skylake X, these were on a higher side. This is the die shot. See the cores, shared cache and the graphic processor. Seventh generation was codenamed Kaby Lake, released in August 30th, 2016. Again made with the 14 nanometer process and having almost similar cache sizes. This is the die shot. This is the cores, GPU, interconnects and the system agent and controlling functions. Each generation was the Coffee Lake, released in 2017, manufactured with 14 nanometer process. Again, the cache memories here were almost the same. This is the die shot. It shows us the cores, the connects and the GPU. Higher multimedia capabilities. In generation was the Coffee Lake Refresh, released in 2018, manufactured with 14 nanometer process. It supports 128 gigabyte of RAM. Also supports Optane memory with Pentium and Celeron processor. Pentium memory is intermediate between the processor and the memory, intended to speed up the data speeds on the data bus. The cache memories were in L1, L2 is almost the same, L3 is slightly more. Another 9th generation processor was introduced, codenamed Cannon Lake, with a size of around 10 nanometer. Here the cache sizes increased. L1 is 128 KB, L2 is 512 KB, and L3 is 4 megabits. So there was a doubling in the cache memory. Next, we need to understand the CMOS device scaling challenges. The physical limits in scaling silicon MOSFET has been reached. When you make smaller source and drain, contact resistance tends to increase. The doping within the source and the drain no longer remains uniform. This is known as doping level abruptness. Look at the gate stack. Thus, dioxide is scaled to a level which is around 1 nanometer thickness. This results into tunneling current from the channel to the gate, thereby increasing your off current of the MOSFET. It also results into another phenomena known as gate depletion under the gate, which tends to increase the effective oxide thickness, results into decrease in ion compared to the expected scaled ion. As we had discussed, we are not scaling VDD to the same extent as the physical dimension. For the electric field within the MOSFET tends to increase. This results into mobility degradation and degradation of the reliability of the overall MOSFET. Look at the channel part. Phenomena known as surface scattering comes into picture. The mobility tends to reduce. Effect known as drain induced barrier lowering comes into picture. There is the increase in drain to source leakage. We are operating the MOSFET at room temperature, so this factor Kt by Q tends to limits the subthreshold slope to a value of 60 millivolt per gate. This results into increase in the off current with scaled MOSFET. Also, VGG minus VT tends to decrease. Therefore, ion is less compared to the expected ion. So, what are the solutions? Some solutions are channel engineering. To understand the channel engineering, let's take a large MOSFET shown here. I'm scaling this by just decreasing the gate length. I get the smaller MOSFET. This scaling is improper because I have scaled only the gate length. This results into the depletion region of the source substrate and drain substrate to come close to each other. In such a scenario, the gate loses the electrostatic control of the channel and no longer able to switch off the MOSFET. The continuous leakage current from source to drain. In order to remove this issue, use what is known as channel engineering. Halo dopings, as you can see here, and we put a threshold implant very close to the area under the silicon oxide. So we reduce the size of the source and drain which tends to reduce the size of the depletion region. We try to understand how to eliminate the tunneling current through the gate oxide. Now the channel current is proportional to the oxide capacitance multiplied by VGS minus VT multiplied by the electric field at the source multiplied by the mobility of the carriers at the source when they are getting injected into the channel. Now historically, the oxide capacitance has been increased by decreasing the gate oxide thickness. It can also be increased by using a higher K dielectric. The drain current is proportional to the oxide capacitance, which in turn is proportional to the dielectric constant K divided by the thickness. Now, all the scaling has been focused on reducing the thickness of the gate dielectric. Now for a smaller MOSFETs, the focus is on increasing the dielectric constant K. So today if we see, using a silicon oxide as your gate oxide, it has a thickness of 20 angstrom, typically a value of 4. At an equivalent oxide thickness, what I can use is silicon nitride, which has a K value of 8, thickness of 40 angstrom. Since I have doubled the value of K, the thickness of the oxide also tends to increase. This helps us in reducing the tunneling current from the channel to the gate. To further increase my K value to 20, the thickness becomes very large. The tunneling current will be almost eliminated. However, the electrical working of all these three MOSFETs will be the same. Higher thickness tends to reduce the gate leakage current. Also, in the larger MOSFETs, we were depositing the poly on the oxide. Now we are depositing the metal on the oxide to avoid what is known as polysilicon depletion, boron penetration through the thin dielectric during fabrication. We scale the MOSFET. Source and drain also gets scaled, and we need to make shallow source drain regions. This tends to increase the contact resistance. So one of the solution is to make shallow source drain towards the gate, normal drain and source away from the gate. This is why we get these two extensions of source and drain very close to the gate. Second solution is to fabricate source and drain which are elevated compared to a normal MOSFET fabrication. Third solution is to have silicide deposited on the source and drain to improve the contact resistance. Fourth solution is to replace the source and drain by metallic source and metallic drain, also known as Schottky source drain MOSFET. The mobility of the electron and holes tends to degrade. So this mobility can be improved by providing uniaxial stress. For NMOS, we provide a tensile stress on the gate, as shown in the diagram. For a PMOS, we provide a compressive stress, shown here. Now, this is a graph of I off versus I on PMOS. It shows us that for any given I off, say I e raised to the power of 7, the on current tends to increase for a tensile stress. Blue curve is for the tensile stress MOSFET. The PMOS, red curve is for a compressive stress MOSFET. Again, for a given of IE to the power of -7, I find that my on tends to increase. By providing stress on the gate, we are able to increase the mobility in the channel. Next, we look at the CMOS power challenges. the MOSFETs have scaled from 0.25 micrometer node to 45 nanometer node, we observe that the power dissipation has increased. In this bar chart, the green part represents the active power and the blue part represents the leakage power. If we see 25 micrometer node, power dissipation was mainly due to active power. In 45 nanometer, we observe that leakage power dissipation has become more than the active power dissipation. This is because the I-off tends to increase with scaling in MOSFET. As we scale over the years from 72 to 2010 and onwards, the power dissipation in the processors have been increasing and has become a big challenge for the design engineers. Solution 1 is to use cooling fins and chip fans as shown in the figures. You have the processor and you put a fan on top of that to remove the heat. Solution 2 is used to have multiple core in one package. Solution 3 is at design level where you switch off the circuits which are not in use and give power to only those circuits which are active. This is the Intel roadmap for scaling. Intel has scaled up to 22 nanometer node wherein the gate length is something like 15 nanometers. These are the MOSFETs at various technology nodes. 65 nanometer process, we have a gate length of 30 nanometer. At 45 nanometer technology node, we have a gate length of 20 nanometer. At 22 nanometer technology node, you have a gate length of 15 nanometer. At 22 nanometer process, you have the gate length of 10 nanometer. This is less than the size of a DNA in our body. Devices have scaled from 19 nanometer up to 22 nanometer. This process over the years has been known as CMOS evolution. Beyond this, as we go to 7 nanometer, 5 nanometer and 3 nanometer, we need some innovative solution. This is also known as revolutionary CMOS, wherein novel materials like nanotubes, nanowires are used to improve the functionality of the device. Beyond this 11 nanometer node, we will require something really exotic, something really different, like spintronics. And this part will no longer be the CMOS. CMOS will typically end at around this technology node. So now the major question that we have is extending CMOS and what are the alternatives to CMOS. Let us see how we first extend the CMOS. Extend the CMOS to smaller technology nodes. We need to use novel transistor structures and material integration for scaling Planar bulk silicon MOSFETs. In order to improve the electrostatic and the contact resistance, double gate structure can be used, a surround gate structure can be used. Instead of having a doped source drain, we can have Schottky source drain. For the channel engineering, we can have high mobility material like strained silicon, silicon germanium, germanium, etc. Now to extend the CMOS functionality via the new integration technology, what is proposed is three-dimensional integration, which we will be discussing a little later. And beyond this, we are looking for new devices which will tend to replace the CMOS, should be compatible with the existing CMOS fabrication fabs. The problems with the MOSFETs is summarized as Problem 1 is poor electrostatic. Means the gate does not have a very good control on the channel. This tends to increase the I. The solution is we can use double gate, gate and a bottom gate. This retains the gate control over the channel and minimizes the off-state drain to source leakage current. Problem 2 is poor channel transport. This decreases the I. So we can use high mobility material in the channel. This will increase the mobility as well as the velocity of the ejected electrons from the source. We'll get high current drive and low intrinsic delay. Problem 3 is source drain parasitic resistance, which tends to decrease the ion. Instead of using the semiconductor source and drain, we use metallic source and drain using as a Schottky functions. Problem 4 is a gate leakage. So this is solved using the high K dielectric material, which tends to increase the thickness of the oxide by reducing the gate leakage. Problem 5 is the gate depletion, which tends to increase the effective oxide thickness. Instead of using poly on the dielectric, use a metal gate on the dielectric. This will tend to increase your ion. You will get a high drive current for the MOSFET. This is a bulk MOSFET. In this bulk MOSFET, if we see the depletion region depicted in red are very close to each other, and this results into source to drain leakage current. For the working of a MOSFET, current is flowing very close to the oxide layer. Deeper inside the bulk region, there is no current flowing. The deeper part of the bulk, I can replace it with SiO2 layer, making the channel very small. This structure is known as silicon on insulator MOSFET. We get is an ultra thin body single gate silicon on insulator MOSFET. Other solution is to have gate 2. You can see here, same structure is there. SiO2 and silicon substrate is removed and gate 2 is added here. This tends to improve the control of the gate on the channel. Now, it's easy to say that we will add the second gate. The question is, how do I do it in a bulk manufacturing process? To make double gate MOSFET structure, the channel which is horizontal for the bulk MOSFET is flipped and made vertical, as we can see in this vertical FET structure. It was fabricated in Stanford with the help of ATN. This is the vertical channel. These are the gate contacts, and one of the contact is finally given to the this is the source and this is the drain. Solution provided by UC Berkeley was double gate FinFET, wherein they fabricated a three-dimensional structure, a three-dimensional channel, and then the gate oxide was deposited on it. Intel came up with its own solution, tri-gate FET. This is our channel, which is raised above the horizontal, and the metal as well as the oxide is deposited on it. So for the channel, there is a two contacts. One is on the left side, one is on the right side, as well as on the top. That's why we call it as a tri-gate FET. He was a pioneer in device scaling. At 45 nanometer node, they manufactured the MOSFET with high K dielectric and metal gate in 2007. They could manufacture MOSFETs at 32 nanometer in 2009. They manufactured MOSFETs at 22 nanometer node, which was the world's first three-dimensional transistor in high volume, and this happened in 2011. The third generation Intel Core processor was the first high volume chip to use the three-dimensional transistor, which are popularly known as FinFETs. We try to look at the alternatives to MOSFETs. One of the problems with the MOSFET is that the subthreshold slope is limited to 60 millivolts per decade. So as my technology node decreases, subthreshold voltage does not decrease. VT tends to decrease, which tends to increase my IF. This is the problem which resulted into search for new devices to replace the MOSFET. MOSFET is scaled. Subthreshold slope does not scale beyond 60 millivolts per decade. We scale the VDD for low power and delay. Results into scaling of VDD in order to maintain the gate overdrive, as we can see in this graph. Lower VT definitely gives us higher ion. However, a lower threshold voltage also leads to higher off current. The leakage current increases between the source and drain, resulting into high static power dissipation. This is all because of the limit of 60 millivolts per decade, which is there in MOSFET because of thermal injection. The question is, can we beat 60 millivolts per decade limit and get a device which will have a characteristic shown here by 2? It is having a subthreshold which is less than 60 millivolts per decade. Tunnel FET is one of the devices which can give us a subthreshold slope which is less than 60 millivolts per decade. The structure of tunnel FET is similar to that of the MOSFET, except that the source and drain are made up of different doping. Source is say P plus and the drain is N plus. Apply a gate voltage, there is a band bending which occurs. Because of this band bending, the electrons from the source tunnel to the channel and the source to drain current tends to flow. The advantage of tunnel FET is low subthreshold swing and low off current. Along with the low off current, also get low on current, which is a big problem for tunnel FET. Challenges involved in designing tunnel FETs are need to have highly abrupt junction so that tunneling takes place here. We require good alignment of the gate edge to the source doping. Ion decreases linearly with any gate overlap, underlap at the source edge. IMOS or impact ionization MOSFET is also another device which gives us a subthreshold swing of less than 60 millivolts per decade. The structure is similar to that of the tunnel FET, except there is a gap created between the source and the edge of the gate. Whenever we apply a high gate voltage, high electric field is generated in this gap. This high electric field results into impact ionization in this area. Large current flows from the source to the drain. The alternative to CMOS, the graphene and carbon nanotubes. Andre Glenn and Konstantin Novoselov managed to make dimensional graphene ribbon in their labs, and for this work got a Nobel Prize in Physics in 2010. Graphene, the atomically thin crystal of carbon, which is stronger than steel but flexible, is transparent for light and conducts electricity. It is also called gapless semiconductor. This image, the dark part which is there is the graphene, and these are the contacts. Graphene has a honeycomb structure as shown in the image. Carbon nanotube is nothing else but a rolled up sheet of graphene shown in this image. Graphene has a two-dimensional periodic honeycomb structure as shown here. It inherits all the good properties because of sp2 hybridization bonds. What is this sp2 hybridization? You see the carbon structure. It has one s orbital which is completely filled with electrons, s orbital which is completely filled with electrons, and three p orbitals, out of which two are filled with electrons and one is vacant. As shown here, one s orbital, there are three orbitals out of which two are filled and this red one is not filled. S and p orbitals combine together to form three sp2 orbitals and one orbital remains as it is. This is the diagram showing the partial distribution of these orbitals, the three sp2 orbitals and one p orbital. So this is discussed. S orbit combines with x and 2py to give us the sp2 hybrid orbits. And the two carbon atoms in a graphene forms a bonding. Bonding between the sp2 orbitals gives you the sigma bonds which are strong bonds. And the bonds between the z orbitals gives you the pi bond which are weak bonds. These weak bonds are the ones which contribute towards the conductivity of the graphene. Here you have the sigma bonds on top and bottom, and in between you have the sp2 bands. These bands gives us the conductivity of graphene in this type of a band structure where there is absolutely zero band gap. Orbitals arise from electrons that are weakly bound to carbon atoms. These electrons contribute to conductivity as small amount of energy is required to release them for conduction. Sigma orbitals arise from electrons that are strongly bound to the carbon atoms. They play a role at higher energies. The properties of graphene are: it is the strongest material in the universe, it has good conductivity, it has superior thermal and optical properties, it has excellent tensile strength, it is relatively transparent, and it is impermeable to most gases and liquids. The carbon nanotube is nothing else but the rolled up sheet of graphene, and they can be classified into two categories: the single-walled nanotube and the multi-walled nanotube. The multi-walled nanotubes can be further classified as the Russian doll and the parchment. CNT is formed by wrapping a graphene sheet along a preferred axis which is characterized by a index n, m. If this n, m has a value of n, 0 as shown here on this axis, what we get is a zigzag pattern at the end of the carbon tube. This is the pattern at the end of the carbon tube. And this type of carbon tube is metallic in nature. This index is n, n as shown here across the diagonal. You get a armchair pattern at the end of the tube. The characteristics of this is metallic if n is equal to 3p, else it becomes a semiconductor. The index is n, m is other than these two axes. The pattern which we get is chiral. It is metallic if n plus m divided by 3 is an integer, else it becomes a semiconductor. The high quality defect-free carbon nanotubes can be manufactured, which gives properties like high tensile strength, high current density, superior thermal and optical properties. Semiconductor carbon nanotubes. Their properties can be altered by doping in a way similar to the silicon semiconductor. By default on manufacturing, the undoped CNT is a p-type due to self-doping caused due to curvature of the tube at nanoscale and commensurate effect on atomic bonding. Doping done by exposing CNT to certain elements or by inserting molecules inside the tube. This is the image of a carbon nanotube and this is the image of a carbon nanotube field effect transistor. The structure is similar to that of the MOSFET except the channel is replaced now by a single carbon nanotube. This is one structure, single channel carbon nanotube. This is a multi-channel carbon nanotube FET. The channel is replaced by multiple CNTs. Advantages are it has better control over channel formation, better thermal voltage, better subthreshold slope, high mobility, high current density, and high transconductance. Other alternative to CMOS is the organic semiconductor. It was first fabricated in 2000 with 864 transistors. It is low cost, lightweight, rugged, flexible electronics. It is not a competition to silicon. It goes where silicon cannot follow. That is where flexible devices are required. Applications are identification tag, low-end data storage, smart card, emissive display, electronic paper, distributed computing, toys, clothes, etc. Even scaling the device, that is the MOSFET, but scaling MOSFET, is it sufficient? Along with the MOSFET, we also need to scale the interconnects, the contacts, the isolation, etc. These are the factors which are now dominating the evolution of integrated circuits. Look at the scaling of the device isolation. Locos, image is shown here, is a bird's beak which occupies a large area. It is a hindrance to making a smaller IC. This locus type of isolation is replaced by trench isolation to save on area. This is further replaced by shallow trench isolation to save on the process. Come to the chip interconnect scaling. As the device dimensions are reduced, the dimension of the interconnect are also reduced. Scaling to smaller dimension reduces the cross section of the interconnects, thereby increasing the resistance, inductance and capacitance of the interconnect. Large wire when scaled becomes a smaller wire with a smaller interconnect. As we see here, the technology nodes have scaled from 180 to around 60 nanometer. Typical gate delay has reduced, but the interconnect delay has been increasing. To decrease the interconnect delay, we need to use better materials, that is metals with low resistivity and dielectrics with low P. The advances in the backend technology. In 1970s, polysilicon gate was used and aluminium was used for interconnects. In 1980s, aluminum alloys were used, silicide contacts were used for making the interconnects. In 1990, layered aluminum, titanium silicides were used along with CVD tungsten plugs. This shows us a 5-layer interconnect using aluminum technology, and this shows us a 6-layer interconnect using copper technology. Now, in order to decrease the interconnect delay, innovative solutions are looked at. One of the solutions is the three-dimensional integration. For a two-dimensional system, all the blocks distributed on the same plane as shown here. Suppose I need to make a connection between the microbattery and the MEMS. I need to run the wire right across horizontally and then vertically as shown here. It becomes a very large area, very long interconnect. In order to reduce the length of this interconnect, what we do is we cut blocks, stack them one on top of the other, giving us a three-dimensional system. When I'm doing the interconnects, wires are not just running horizontally but also vertically, which tends to give us a shorter wire for interconnect. So this reduces the chip footprint, the chip size reduces, it replaces the long horizontal wires by short vertical wires. Interconnect length decreases and therefore your resistance, inductance and capacitance reduces. The reduction in power supply, the gate delay also tends to reduce. Other option is to use optical interconnects on the chip and in between the chips. This has been demonstrated by MIT, that is Massachusetts Institute of Technology of USA. Concluding, technology has progressed. Initially we had the bulk CMOS. From bulk CMOS got the fully depleted silicon on insulator CMOS. We got the strained silicon CMOS. We got the three-dimensional devices to get our double gate structure. The channel was replaced by silicon germanium or germanium material with better performance at smaller dimensions. Along with the reduction in the dimensions of the MOSFET, interconnects were also scaled. Optical interconnects were also demonstrated in the lab, not commercially. We have managed to get MOSFETs and integrated circuits working at high speed. Beyond 22 nanometer node, as we move towards the dimensions of 2 nanometer, the era of nanotechnology starts. Here we use the single electron transistor, molecular devices, spin devices, and so on. Finally, I give acknowledgement to the different sources from which I have accumulated this data for this PPT. First, I give the acknowledgement to Electrical Department, Indian Institute of Technology, Bombay. Second, to the Stanford University, Professor Krishna Saraswat. Intel website, Tokyo University, Professor Aiva, and online resources from the net. This is some of the references which I have taken. Thank you for your attention.
Thank you, sir, for providing the insights in integrated circuit technology. To our participants, kindly note the next session, that is tomorrow, will be scheduled sharp at 10:30 a.m. Also to note that there are 3 sessions tomorrow. Till then, stay safe. Thank you.